Gauss theorem helps to calculate electric flux out of a closed surface enclosing charge. This method is easier than applying Coulomb's law. Hello, welcome to Guidance Education channel. In this video, we are continuing Class 12 Physics, Chapter 1, Charges and Fields. The topic discussed in this video is of great importance from examination point of view, so watch the video completely without skipping. And if you think the video is useful, like the video and share it with your friends who may also be benefited. If you have not subscribed my channel, do subscribe it now and also press the bell button so that you get intimated as soon as videos are posted. Thank you. Let us see the subtopics that are discussed. The topic discussed in this video is Gauss law. We will do definition of Gauss law, formula of Gauss law, mathematical expression of Gauss law, and finally proof for Gauss law. Okay, come, let us start.
In this video, we will discuss Gauss theorem or Gauss law as it is known. This law helps to calculate electric flux out of a closed surface enclosing charge. The closed surface can be of any shape. We will select here a sphere. This is a sphere closed surface enclosing charge. This is the charge inside it. On a paper, we can represent the sphere only as a circle. But the sphere is more or less like this in 3D. The charge is well inside the sphere in the center of it and not on the surface. The electric field of the charge inside the closed surface radiates outward in all directions along the radii and pass outside the closed surface. The sphere can be assumed to be formed of a large number of, say, n number of area elements which are also small spheres called dA. It may be numbered as dA1, dA2, dA3, dAn. In this diagram, I have shown only a few numbers of small dAs. It is assumed that several more of them are present throughout the sphere. Look at this diagram. This is like a cross section of the sphere. Only the peripheral area elements are shown. Electric field lines radiating from the charge pass out through the area element. Several field lines may pass out of each area element. The direction of the electric field line and direction of the area vector of each area element are in the same direction. It is true for each area element. So, there is a net flux on the closed surface. Now, we need to calculate the electric flux out of the closed surface enclosing charge. How to do that? Gauss theorem gives the solution. That too in a very simple and easy manner. I have already posted a video on a closed surface resting in external electric field. That is, the source charge is outside the sphere. In this case, the source charge is inside the closed surface. Net flux is not equal to 0. For a closed surface resting in external electric field, the net electric flux is equal to 0. If you have not yet watched that video, click the I button to watch that. Coulomb's law can be applied to calculate the electric flux out of a closed surface enclosing charge. Electric flux phi is equal to E dot dA. That is E dA cos theta. But then we will have to calculate electric flux due to each little small area element, that is dA, like dA1, dA2, dA3, dAn, etc. and then integrate the whole thing, which will be very tiresome and long procedure. Gauss law simplifies the whole thing. Gauss conducted studies on this and came up with a very simple and easy formula to calculate flux out of a closed surface enclosing charge. Let us see the law first. The law states that electric flux out of a closed surface enclosing charge is equal to 1 by epsilon naught times the charge enclosed by it. Epsilon naught is the permittivity of space. It is a constant. The charge enclosed by it is represented by the letter Q. Mathematical representation of Gauss law. Electric flux is equal to 1 by epsilon naught into Q, or Q divided by epsilon naught. The flux is out of closed surface enclosing a charge. This is a very simple formula. That is why it is widely used and has lot of practical application. If Coulomb's law is applied, then also we can get the same result. But this is easier and fast. How can we prove this law? Let us see that. Let us prove Gauss law. We may use two methods. Both methods are very simple. What is the mathematical representation? Phi is equal to Q by epsilon naught, which is 1 by epsilon naught into Q. We have to prove this. What is the general formula for phi? It is E dot dA. For dot product, it is E dA cos theta. Let it be. We have selected a spherical closed surface. It is assumed to be made of large number of small area elements which we named as delta A1, delta A2, etc. up to delta AN. We will apply the formula and find out the electric flux through each area element separately and see the final expression. For area element A1, we can write phi delta A1 is equal to, substituting for electric field, 1 by 4 pi epsilon naught Q by R square into dA. What is the area of a sphere? It is 4 pi R square. So, into 4 pi R square. This 4 pi R square and 4 pi R square there get cancelled. What remains is epsilon naught and Q. So this becomes equal to Q by epsilon naught. Let us try the next one. That is delta A2. Phi delta A2 is equal to the same thing, 1 by 4 pi epsilon naught Q by R square into 4 pi R square. This 4 pi R square is the area of the area element A2, A1, A3, AN, etc. 4 pi R square get cancelled. What remains is again only Q by epsilon naught. You get the same expression. For any number of area elements like this, we have considered there are n number of area elements. The value will be a constant, that is Q by epsilon naught. It proves that flux out of the whole sphere, that is for the closed surface, will be equal to Q by epsilon naught, which is nothing but 1 by epsilon naught into Q. This is what the law says. So we have proved that law by this method. Now we will see the second method. The general formula is phi is equal to E dot dA for delta A1. Phi delta A1 is equal to 4 pi epsilon naught Q by R square. We have substituted for electric field dot delta A1, that is area. In a similar way, we can write the expression for electric flux out of all the other area elements like delta A2, delta A3, etc. up to delta AN, and then integrate the whole thing. all these expressions will be the same but for one expression, that is the area element only, that is dot delta a1 dot delta a2 dot delta an closed integral phi delta ai, the limit of I is 1 to n, is equal to phi for the whole sphere, that is closed surface. 1 by 4 pi epsilon naught q by r square is common for all the expressions, so it need not be integrated. It can be taken out, is equal to 1 by 4 pi epsilon naught q by r square integrating delta ai, the limit of I is again 1 to n. Integrating this will be equal to the whole area of the sphere, that is 4 pi r square. Okay. So it becomes phi for closed surface, that is electric flux, is equal to 1 by 4 pi epsilon naught q by r square into 4 pi r square for the whole sphere. This 4 pi r square, this r square and 4 pi all get cancelled, and what remains is q by epsilon naught. So phi for closed surface is equal to q by epsilon naught, which is again equal to 1 by epsilon naught into q. That is what Gauss law says. So we have proved Gauss law by the second method also. It is all very simple, not at all difficult. I hope this was of great use to you, and we will meet in the next video with applications of Gauss law, which is also very important. Till then, bye and thank you.